This is your presenter, Asloob Mudassar, and I am presenting slide number 18J of the course in Atomic and Molecular Physics. In the today's lecture, I shall be covering the following topics: spectra of diatomic molecules, transition, matrix elements, vibrational rotational transitions. This is the 10th lecture of the series on molecular physics, and it is in continuation of the previous 9 lectures starting from 18A to 18I. So you should consult those 18 lectures first in order to understand the current lecture. Spectra of diatomic molecules. Consider the molecular transition between two molecular states, ith state and kth state. Here you see that I am considering two molecular states, and I am also considering a transition between these two states. So EI is the energy in corresponding to the ith state, depending upon the quantum numbers Ni, lambda I, Vi, Ji. Lambda I, this is capital lambda I, which is the projection of the orbital quantum number L on the internuclear axis or on the Z axis. N is any number which indicates that which level is higher in number and which level is lower in number. So it tells us roughly about the energy of the level. For higher corresponding to higher N, the level will have higher energy. But don't confuse this Ni with the principal quantum number. And similarly, I have the energy state, and corresponding to the kth wave function, I have the energy Ek, again depending upon 4 quantum numbers. Here the quantum number Vi stands for the ith vibration level, Ji stands for the ith rotational level, and on the right hand side I have Vk, which means that it is the kth vibrational level, and Jk means it is the kth rotational level. The transition frequency, which is given by V, is equal to delta E over H. That is, the delta E is actually the difference between two rotational levels divided by H will give you the transition frequency between those two levels. So this depends on the transition probability, which is proportional to the absolute square of dipole matrix elements. So you see that the transition probability will depend upon the square of the dipole matrix elements, which is MIK. That is the absolute square of MIK. So transition probability will depend upon the absolute value of MIK. The transition energies depend on the electronic, vibrational, and rotational structure of the molecules. And the matrix elements are complex. So you see that when we are talking about the transition could be from one electronic state to another electronic state, or from the same electronic state between the levels of the same electronic state. And the vibrations level could belong to one electronic state or the other electronic state, or the vibration levels may correspond to the same electronic state. And similarly, we have the rotational states. Rotational states could correspond to different vibrational states or to the same vibrational states. So you see that all these electronic, vibrational, and rotational states will depend upon the structure of the molecules, and the matrix elements are generally complex. The molecular spectra related to these matrix elements will be discussed in greater detail. Because you know that our transition probability will depend upon the matrix elements, which is the dipole matrix elements, then of course we need to discuss in great detail. For spontaneous emission, which is also known as the fluorescence spectra, the emission probability of the transition from the ith state to the kth state. You see that here I am talking about emission spectra. It means that the ith state is higher in energy in comparison to the kth state, and these two states are actually the electronic states of a molecule. For spontaneous emission or for the fluorescence spectra, the emission probability of a transition from the ith to the kth state is given by the Einstein coefficients AIK. And AIK is equal to 2/3 multiplied by cube of omega ik divided by epsilon naught c cube h, and then multiplied by the absolute square of mik. So you see that in the expression of aik, you counter the absolute square of mik. So if mik is determined, then of course this coefficient, which is the Einstein coefficient for the emission probability between the transition from the ith state to kth state, will be known. For absorption or stimulated emission, so you see that here I am talking about absorption and stimulated emission. Of course, these two emissions are dealt in a very similar manner. So for absorption or stimulated emission of radiation, the transition probability, which is PIK, is the transition probability between the ith and kth level, is equal to BIK multiplied by W of VIK. Again, you see that BIK are the coefficients, Einstein's coefficients, and W of VIK, what it is that it is, so this PIK is proportional to the spectral energy density W of V. So W of V is actually the spectral density of the radiation field that is either absorbed or emitted during the absorption or the stimulated emission process. This PIK has an expression given by, which is equal to pi over h square multiplied by E naught square, and then the absolute square of integral of psi k star E dot P, the product of E and P, and then psi A, and then d tau. So you see that here we are considering the two wave functions psi k and psi I, which are the wave functions corresponding to the ith electronic state and the kth electronic state. E hat, which is the unit vector, is equal to the value of vector E divided by the absolute value of magnitude of vector E. So this I hat is actually a unit vector in the direction of the electric field of the electromagnetic wave incident on the molecule. So this capital E is the vectorial form of the electric field which is incident on the molecule, and E hat is actually a unit vector in the direction of the electric field of the electromagnetic wave incident on the molecule. The transition probability therefore depends upon the scalar product. So you see that the transition probability, which I have written PIK, will depend upon the product E dot P of the electric field vector and the electric transition dipole. So you see that I have defined E, small e, because the small e hat is actually a unit vector, and now I am going to define P. So E, small e, as actually the electric field vector of the incident beam, and the electric transition dipole moment is P. So P is the electric transition dipole. P, which is the P vector, is equal to E into R vector of the molecule. Here you see that I am writing, since I am discussing in equation number 188 the electronic state, for the electronic state the electric dipole or the electric transition dipole is given by the expression that P vector is equal to E times R vector, where E is the electronic charge on the electron that we are considering, and R is actually the radial distance of the electron from the center of mass. And you know that when we are talking about a single transition, then of course a single electron is involved in that case. And that is why P vector will be equal to the single electron charge E multiplied by the radial distance of the electron, or the radial vector of the electron. Transition matrix elements. Dipole matrix element between two molecular states psi I and psi k are defined by, so MIK, which is the dipole matrix element, is equal to the double integral of psi I star vector P And you know that vector P is actually the electric transition dipole P vector, then psi k, then d tau L. This is d tau L actually corresponds to the electron, and the d tau N corresponds to the nucleon. And you know that this is the double integral because the wave function psi will consist of two wave functions. That is the electronic wave functions, pure electronic wave functions, and also to the nuclear functions. So here psi I is actually the wave function corresponding to the ith electronic state, and psi k is actually the wave function corresponding to the kth electronic state. Integration of the electronic coordinates extends over all three times Za plus Zb, that is including all electrons. So Za plus Zb will give you the number of all electrons present in a molecule, and each electron will have three possibilities, which will have three axes, or will have three axes. So that's why it is multiplied by 3. Because in order to specify the position of an electron, we need three coordinates x, y, and z. So that's why this number is 3. So you see that it represents actually the total number of degrees of freedom required to specify all the electrons. 3 multiplied by the number of electrons, and over 6 nuclear electrons. Since we are considering diatomic molecules having 2 nuclei, so each nuclei has 3 degrees of freedom. So corresponding to 2 nuclei, we have 6 degrees of freedom. So let me read this sentence again. Integration of the electronic coordinates extends over all 3 times into Za plus Zb and over 6 nuclear coordinates. Normally, only one electron is involved in the transition, and the integration over d tau L is performed only for that electron. So you see that this integral, the above integral, will be performed only for a single electronic transition. And P, which is the dipole moment of the molecule, which we are here P is actually the dipole moment of the molecule that we are writing. So P vector is equal to minus E times the summation over I, the vector Ri, where Ri stands for the position of the ith electron. And you know that we are summing up all the position vectors of all those electrons, plus the next part belongs to the nuclear part. That is the nuclear dipole transition dipole moment, which is a plus E times Za plus Za times Ra plus Zb times Rb. So this is, you see that I have written these two in a separate form, PL, which is for the electron, and Pn for the nucleon. And you know that the first part up to this one, this part corresponds to PEL, that is the electric dipole, that is electric transition dipole for the electrons, and this part corresponds to the dipole of the nucleon, electric dipole transition of the nucleon. So I have separately written as PL plus PN. Now you see that in this diagram, I am going to specify these parameters. You can see that there is an electron which is revolving about its center of mass coordinates with a radial vector Ri. And you know that there are 2 nucleons with charges plus Za times E, and the other nucleus has a charge plus Zb times E. And you know that from the center of mass, the nucleus A on the left hand is at a distance Ra, and the nucleus B is at a distance Rb from the center of mass. And you know that this is the same equation that I have written in as equation number 190, and I have reproduced over here for quick reference. That is minus E into summation of Ri represents the electronic part of the dipole transition, and the other, which is E times Za times Ra plus E times Zb plus Rb, actually represents the dipole transition corresponding with the nucleons. So this figure actually is the illustration of the nuclear and electronic contributions to the molecular dipole moment. And you know that for this, if PL is the construction, is the contribution of the electrons, and Pn is the contribution from the nuclei. For homonuclear molecules, so you see that for homonuclear molecules, Za is equal to Zb. Similarly, Ra is equal to minus times Rb. And so under this condition, you will see that Pn becomes equal to 0. So for homonuclear molecule, we don't need to take into account the nuclear dipole moment, and only the electric dipole moment or electric transition dipole will be enough in order to find out the matrix elements. Under adiabatic approximation, that is, nothing is entering into our molecular system and nothing is leaving from our molecular system. So under adiabatic approximation, the wave function can be represented by, that is, we can separate out the wave function under the adiabatic approximation. So this is the molecular wave function psi of r comma capital R, and on the right hand side I have capital phi of r comma r, which is the electronic wave function, and then multiplied by x chi n as a function of r. So chi n is actually the nuclear wave function. So here in the paragraph, I have defined phi, capital phi of r comma r is actually the electronic wave function of the rigid molecule. That is, the distance between the two nuclei is fixed with r fixed, and chi n as a function of r is the nuclear wave function and depends on the nuclear coordinates. So you see that now we have the molecular wave function specified as the product of two wave functions, the electronic wave function phi, capital phi, and the nuclear wave functions capital chi under the adiabatic approximation. Inserting equation number 190 and 191 into equation number 189, which is the, so let me show you those equations. This equation number 191, this is equation number 190, and this is the equation number 189. So inserting equation number 190 and equation number 191 into equation number 189, we get this equation, that is equation number 192. So you see that here I have plugged in the values of PEL plus PN, and then of course I have also substituted the product of wave functions phi I star multiplied by chi n star, and both are corresponds to the ith electronic state, and then I have phi k and chi n comma k. So chi n stands for the nuclear wave function and k stands for the kth electronic state. So you see that this wave function corresponds to, this product of wave functions corresponds to the kth electronic state, and the product of ith wave functions, the product of these two wave functions corresponds to the ith electronic state. And then you see that I am integrating with respect to d tau L and d tau N. And you can see the transition dipole due to electron and due to nucleons is present in the integral. Now you see that we can separate out the two integrals. One integral will contain PEL, that is the electronic dipole, that is the electronic transition dipole, and the other will contain PN, which is the nuclear dipole transition. So now we have separated the two transitions, we have separated the transitions involving electronic part and the transitions involving nuclear part. These two integrals have been separated. And together these two integrals will form the matrix elements of the MIK. Now you see that we have to analyze and solve these integrals under some approximations. We present the two cases next, and for that we see the figure on the next page. This is the figure. Rotational and vibrational levels in two different electronic states of a diatomic molecule. So you see that here in this diagram I am considering two electronic states. One is the electronic state E1, and you know that in the superscript I have written EL. So this is the first electronic state as a function of R, and EL2, E2EL as a function of R is the second electronic state. So these represent the two electronic states. And in the lower electronic state, you can see that the horizontal lines, which are blue in color, these are the horizontal lines which are intersecting the red color, and these are horizontal lines intersecting the curve are actually the vibrational levels. And you know that I have specified them as V double prime 0, V double prime equal to 1, V double prime equal to 2, V double prime equal to 3. So I am considering these four vibrational levels. And in between these vibrational levels, there are black levels which indicates the rotational levels between two vibrational levels. So between any two vibrational levels, I have specified these one as the rotational levels. So I have also written rotational levels E double prime as a function of J double prime. So these small blocks containing black lines are actually the rotational levels, which can be represented by E double prime as a function of J double prime. And the vibrational levels will be specified with V double prime. So in the lower electronic state, the vibrational levels will be specified with the V double prime, and the rotational levels will be specified by the quantum number as J double prime. And you know that I have specified E D double prime also, which is the value of the energy that you will supply to dissociate the molecule. So ED double prime is actually the dissociation energy of the molecule. So if you provide in the lower electronic state an energy equal to E double prime, then of course this molecule will be dissociated. And you know that corresponding to this lower electronic state, I have specified the equilibrium separation between the two nuclei represented by RE double prime. And corresponding to the second electronic state, the equilibrium distance, which is the minimum, occurs at the minimum point, is specified by the Re single prime. So you know that in the second electronic state, all the values are specified by single primes. All the vibrational levels are specified by single prime. V single prime equal to 0, V single prime is equal to 1, V single prime is equal to 2, V single prime is equal to 3. These are the vibrational quantum numbers. And then you see that the rotational quantum numbers are also specified as EJ as a function of a J single prime, where EJ is actually the represents the energy of the rotational levels, and J single prime stands for the different rotational levels over here. And you know that these rotational levels have also been specified with a slightly shift in over here, so that these can be well identified from the previous copy. If I have drawn them in the same line, then of course the discrimination between them will be different. So I have specified these rotational levels separately at each vibrational level. So between two vibration levels, there could be many rotational levels. And you know that this ED single prime is actually the dissociation energy, that if you provide this much energy to the molecule when it is in the electronic state number 2, the molecule will disintegrate. The vibrational energies will be specified by E prime of V prime, E single prime as a function of V single prime, whereas the rotational energy will be specified as E single prime as a function of J double prime. And similarly for the lower electronic state, the vibrational energy will be specified as E double prime as a function of V double prime, and the rotational level energies will be specified as E double prime as a function of J double prime. And you know that these two parts represent the rotational and vibrational levels in two different electronic states of a diatomic molecule. So you see that while I am now going to have some discussions, you can keep this figure in your brain so that you can understand the things that I am going to present. So let's start from the previous things that we have covered a minute ago. That was the matrix elements that depends upon the two integrals. Now let's do some mathematics in order to simplify the MIK. That is, we can find MIK. Either it is possible to find MIK for the electronic part and also for the nuclear part separately, or it is not possible or possible. We present the two cases next, and for that we see the figure on the next page. The figure I have explained to you. You know that in the figure I specified the two levels as electronic level 1 and electronic level 2. You can also consider those two as ith level and kth level, where ith level is the higher level and kth level is the lower level. For example, this energy state E to EL can be specified as the kth state, and the lower state can be specified as the ith state. Sorry, the upper one as the ith state, the lower one as the kth state. The levels I and K belong to the same electronic state. So you see that here we are assuming. So let's assume that I and K belong to the same electronic state. And you know that in the figure that I have shown, the upper curve represents the ith state and the lower curve represents the kth state. But you see that we are considering the same electronic state. The levels, the ith level and the kth level now belong to the same electronic state. That is phi I is equal to phi K. And you know that we use the wave function phi in order to represent the electronic state. Since we are considering the same electronic state, so I have written phi I is equal to phi K. The dipole transition occurs between the two vibrational rotational levels in the same electronic state, say phi I. So dipole transition occurs between the two vibrational rotational levels in the same electronic state, because we are considering the same electronic state. The first integral is 0 because the integrand r times phi I mod square is an ungeared function of electronic coordinates I. That is, the integrand is an odd function in the first integral. That is this integral in the first integral, that is this one. In this integral, the integrand, which is r times phi I mod square, is actually an ungeared function, that is an odd function of coordinates r, because it becomes r times into phi I mod square. And you know that this r, which comes from PEL, is actually a function of x, y, z. So you see that since we are performing the integral from minus infinity to plus infinity, and if the integrand is an odd function, the integral will be equal to 0. So the integral between the limit minus infinity plus infinity gives 0. So under the same electronic state, the first integral will vanish out. The electronic wave function phi are orthonormal. Orthonormal means that they must satisfy this condition. That is the integral of the product of phi I star and phi k with respect to d tau L will be equal to delta ik. If phi I is equal to phi k, then we have this integral is equal to 1. And if phi I if I is not equal to k, then of course the integral will be equal to 0. So the wave functions phi, which are the electronic wave functions, are orthonormal wave functions. That is, they satisfy both conditions of orthogonality and normality, and is given by delta of ik. But you know that in the previous integral that we were considering, integral number 1, that is this integral, it not only contains the phi I, phi k, but it also contains the variable r. And variable r is an odd function. Due to this one, r times absolute square of phi I becomes an odd function or an ungeared function. And the integration between the limits minus infinity to plus infinity will be equal to 0. But remember that phi I functions are the orthonormal wave functions. That is, they satisfy this condition given by equation number 194. Now you see that under the same electronic state, when we are considering the vibrational rotational transition, for the same electronic state, we have found that the first integral in the previous equation will be equal to 0. And then we have this matrix elements Mik is equal to the integral of xi star, and n stands for the nuclear, chi I star multiplied by Pn, nuclear dipole transition, and then chi kn and d tau n. Of course, here again, chi I and chi k belong to the same electronic state with respect to nuclear point of view. The integral depends on nuclear coordinates, of course, because it contains Pn, and also chi I and chi k are the nuclear wave functions corresponding to the same electronic state I and k. Because you see that in the first integral was removed from the previous calculation, that is this integral, that is the first integral was removed because it was equal to 0 for the same electronic state. And since we are considering the same electronic state, so the same electronic state will also be applicable to the second part, which is related with nuclear coordinates. So the integral depends only on nuclear coordinates. Now let's analyze this integral. If the transition occurs between two different electronic states. So you see that for the same electronic states, we found that the first integral was 0 and the second integral related with the nuclear coordinates is given by equation number 195. Now we are considering two different electronic states as depicted in this diagram. For example, in this diagram, we are considering two different electronic states. So if the transition occurs between two different electronic states, the second integral in equation number 193, that is this integral in equation number 193, will be 0 due to equation number 198, that is due to this equation. Because now since we are considering two different electronic state, I is not equal to k. So I and k are different. So delta of ik will be equal to 0. So it means that this integral will be equal to 0. And you know that phi I star and phi k are present in that integral. You can see phi I and phi I star and phi k are present in this in the second integral. So when I and k are different, this integral will vanish out. That is, the second integral will vanish out. And then you see that we are left with the first integral only. And this first integral can be written as this MIKEL as a function of r is actually the integral in the square bracket. So this integral in the square bracket is specified by M as a matrix element of MIK for the electronic system as a function of r. And then of course we have two other wave functions, chi I star and chi k star, belonging to two different electronic states. And of course these are the nuclear wave functions. Now you see that in the first case, when we are considering the transition between the same electronic state, then we get MIK equal to equation number 195. But when we are considering the transition between two different electronic states, then of course MIK is given by equation number 196. Now these two cases will be discussed now. Vibrational rotational transitions. Same electronic state. You know that when we are talking about same electronic state, it means that I am talking about this matrix element, because this was obtained for the same electronic state, transition between the same electronic state. So since same for the same electronic state, different vibrational or rotational levels, that is Vij, the transition from this set of quantum numbers to the transition to Vk and Jk, where these quantum numbers could be different, but the vibrational level is the same, but the electronic level is the same. That is the I and J are, that is I and K are the same. They are not different. That is, we are considering the transition between the same electronic states. We are considering the transition between vibrational and rotational levels of the same electronic state. And the electronic state is specified by the I and K coordinates. The spectrum is in the infrared region. You know that the vibrational quantum numbers are different. Rotational quantum numbers can also be different, but the electronic state is the same. And you know that it will give you infrared region with a wavelength of 2 to 20 micron. For rotational transitions, so you see that here are you considering, here you consider two different vibrational levels and the transition between two different vibrational levels. One vibrational level is Vi, the other vibrational level is Vk. So Vi is lying is the higher vibrational quantum number, and Vk is the lower vibrational quantum number. So the transition between these two vibrational quantum numbers of the same electronic state will give you lambda in the range from 20 to 20 micron. For rotational transition between the same between the same vibrational states, that is Vi and Vk are the same. So you are considering the two vibrational levels which are the same, and you are considering now the transition between rotational levels of the same vibrational levels. Then the rotational spectrum lies in the microwave region, giving you a wavelength of 0.1 to 10 centimeter. So you see that I have given you a specification of the range of different wavelengths when the transitions occur between different vibrational levels. That is this one. And when the transition occurs between different rotational levels of the same vibrational level. The dipole matrix elements for these transition following equation number 190 and 195 are given by. This is 195 and this is 190. P, the value of P. So you can put the value of P from equation number 190 and you can put it in the equation number 195, and then you will get this relation. So this is the matrix element between the I and the K, and I and the K here belongs to the same electronic state, and we are considering the rotation and vibration. That is the rotational transition and the vibrational transitions are being considered in this equation between the same electronic states, and IK represents the same electronic state. And you know that it is given by this one, as I told you that I have used equation number 190 and 195 to get this result. For homonuclear diatomic molecules, Za is equal to Zb, Ma is equal to Mb, which gives Ra is equal to minus Rb, which implies that the matrix element I and K for the rotational and the vibrational transition will be equal to 0. For these molecules, there are no dipole allowed transition because the matrix element corresponding to those dipole transitions is equal to 0. So there are no dipole allowed transitions for the same electronic states for a homonuclear diatomic molecule. So if you are considering a homonuclear diatomic molecule, then of course there will be no allowed dipole transitions for the same electronic states. They may have weak quadrupole transitions. So you see that they may have weak quadrupole transitions. And I don't know whether I am discussing the quadrupole transitions or not, but if possible, I may be considering quadrupole transitions in the next lecture. So the conclusion is that for homonuclear diatomic molecule, the matrix for the same electronic state, the matrix element MIK for rotation vibration is equal to 0, which means that there are no dipole allowed transitions with having the same electronic state. So for the same electronic state, for the homonuclear diatomic molecule, there are no transitions, no rotational transitions, no vibrational transitions. However, weak quadrupole transitions may occur. So you see that that was the case of homonuclear diatomic molecule. Now we are considering the hetero diatomic molecules. For example, CO2, H2O, and H3CH4 are present in atmosphere in small concentration and can absorb infrared radiation reflected by Earth back into space and can increase the atmosphere's temperature, also known as greenhouse effect. Whereas N2 molecule and O2 molecule have high concentration but cannot absorb infrared radiation and are safe for humanity. Let's establish how to determine the spectrum of the heteronuclear molecules in pure rotation and in vibration rotation. That is, we can consider pure rotation, that is from rotation to rotation transition, and we may also consider vibration rotation transition. That is a rotational transition from one vibrational level to another vibrational level. That is the rotation from one rotational level of one vibrational level to some other rotational level of some other vibrational level. So these are what we are going to determine for the heteronuclear molecule. The interaction potential between the two atoms is spherically symmetric. For example, in case of electron revolving around the hydrogen atom nucleus, you see that we have the potential which is a spherical symmetric. Similarly, when we are considering two atoms separated from each other by a distance capital R, then we may consider the potential between them as spherically symmetric. We represent the wave function chi n, which is the function of capital R, theta, and phi in spherical coordinates. So we need to express chi n as in spherical coordinates if we really wanted to solve the integral. So referring to the figure on page number 98, 191, pages 198 and 124, which I cannot show you, which I have covered in one of the previous lectures, then capital R is equal to the absolute value of RA minus RB. RA divided by RB will be equal to MP over MA, and then P is equal to P vector over then the unit vector will be equal to the P vector divided by the magnitude of the P vector. And you know that these relationship, that is RA over RB is equal to MB over MA, can follow directly from the figures I have mentioned. Now the dipole moment Pn is what we are going to determine. So you see that Pn will be equal to P unit vector into the magnitude of P vector. I have written P unit vector on the right hand side. You can see over here, here it is the P unit vector. And here the magnitude of the Pn vector is given by this relationship, that is E multiplied by MBZA minus MAZB divided by MA plus MB multiplied by this R. Because you see that here you have put your reference on one nuclei and you have calculated the nuclear dipole moment for the second nuclei, and then according to that one you have calculated this relationship. So this is the same relationship as you have calculated in fundamental geometry. That is the ratio between the R values of the two different, for example, two nuclei. So E multiplied by this factor, which is multiplied to the value of R, so that R can be correctly recorded and correctly computed using this ratio. So this will be the value of E times this factor multiplied by R will give you the value of P naught, or will give you the value of absolute square of Pn, and then P unit vector is what I have written, where P naught is separately written over here, charge, and then the value of R. This value of R multiplied by this ratio in order to produce a correct value of R between the two nuclei. So you see that putting P naught over here, I have this value of Pn, which is the dipole moment for the nucleon system or for the nuclear system. Now you see that Pn is defined in the using the XYZ coordinate system of the molecular frame. So in order to specify Pn, we shall use XYZ coordinate system of the molecular frame, whereas the electric field vector of the electromagnetic wave, which is incident on the molecule, will be defined in the laboratory frame system, which is the capital X, capital Y, and capital Z system. And you know that these two systems can be linked together. So let me read the caption: transformation from the molecular frame XYZ into the space fixed frame capital X, capital Y, and capital Z. And the transformation between these two coordinate system is shown over here in this diagram with the help of this diagram. You can see that in this diagram I am going to show you two planes. One is the blue plane, the other plane represented by red. So in the blue plane, the blue plane contains x coordinate. The blue plane contains two axes, x-axis and y-axis. These are small x-axis, small x coordinate. So the blue plane represents the xy plane. That is the small xy plane. And the z-axis, you see that is perpendicular to the blue plane. This z-axis is actually perpendicular to the xy plane. That is perpendicular to the blue plane. So I have x-axis, y-axis, and z-axis labeled with blue coordinates x, y, z, and x and y are actually lying on the blue plane. So I am also representing the red plane over here. And you know that this red plane contains axes which have been shown by capital X, capital Y, and capital Z. So the x-axis, which are capital X-axis and capital Y-axis, they are contained or they are lying on the red plane, whereas this Z-axis is perpendicular to the red plane. So I have a blue plane containing the X, Y-axis, small x and small y-axis, and the red plane containing a capital X-axis and capital Y-axis. And their z-axes are respectively perpendicular to the blue plane and the red plane respectively. The xy coordinate system have been marked with black lines, whereas the capital X, capital Y, capital Z axes have been marked with green arrows. And you see that I have also considered a point P in these two planes. And I have shown the projection of a point P on the red curve. And then, of course, I have joined that one to the origin. The origin of the two systems is the same. So let me explain these angles. Alpha is the angle between the small x axis and the capital X axis. So it means that if you rotate the z axis, small z axis by clockwise by an angle alpha, then this small x axis will coincide with the capital X axis. Now look at the angle of beta, which is the angle between small y axis and capital Y axis. So if you rotate x axis, the small x axis, by an angle counterclockwise by an angle beta, then y axis will coincide with capital Y. Similarly, I have shown the angle gamma between the small z axis and between the capital Z axis. So you can rotate the z axis small z axis about the by an angle gamma to coincide it with the z axis. And this rotation can be implemented through x axis. So you see that I have shown these. I have shown critical angles. So you see that theta is actually the angle between the vector P and the z axis of the laboratory frame axis, which is capital X, capital Y, capital Z. I have shown the value of theta, which is the vector P makes with the capital Z axis. Actually, this y I think that should go from the X axis to this dotted line. This dotted line. So this value is actually phi. So theta and phi, you know that two values are required in a spherical coordinate system. One is the value that a vector makes with the capital Z axis, and other the value that the line joining the origin to the projection of a point P on the plane, on the xy plane, is determined by the angle phi. So angle phi is not this angle, but actually the angle phi is the angle that this dotted line, this dotted line makes with capital X axis. So you see that I have explained all these coordinate systems, X axis, Y axis, and Z axis, which is the molecular frame of system. I have given a proper description of this one, and I have also specified the capital X, capital Y, and capital Z axis coordinate system, which is the laboratory frame of system. And I have also specified the angles by which we can rotate one coordinate system to coincide it with the other coordinate system. And alpha, beta, and gamma are the angles by which we can rotate the smaller coordinate system to coincide it with the laboratory frame coordinate system. The necessary angles have also been specified. So you see that I am also going to show you another picture. Capital X, capital Y, capital Z are shown, and any vector P is shown over here. So this P will make an angle theta with capital Z, and this P, the projection from its head onto the XY plane, and then the joining of this projection to the origin will make an angle phi with the x-axis and with this point. So phi angle is also shown. And you know that the three coordinates, orthogonal components of a vector P, which is Px, Py, and Pz, are also shown. And you know that the caption of this figure is orientation of a molecular dipole moment P in a space fixed coordinate system. So I am going to show you the molecular dipole moment P in a space fixed coordinate system. So let me go through these paragraphs very quickly. Transformation from small xyz system to the capital XYZ system can be achieved through three rotations about XYZ axis by an angle alpha, beta, and gamma respectively. Orientation of vector P in the XYZ axis can be defined by theta and phi, and in the capital X, capital Y, Z system can be defined by capital theta and capital phi. So for the capital X, capital Y, capital Z system, the two angles will be defined by capital theta and capital phi, whereas in the small XYZ system, the orientation of a tail will be defined by angle small angle theta and small angle phi. So if you want, you can make a correction to this figure. If we are considering a capital X, capital Y, capital Z, we need to specify the angle capital theta and capital phi. For a diatomic molecule, Pn is directed along Z axis. So you see that, remember that for a diatomic molecule, Pn is directed along Z axis or the molecular axis, and small theta will be equal to 0. The components of a Pn in the space fixed X, Y, Z coordinate system are this. So you see that when vector P coincides with the Z axis, the angle theta, this small theta, which it makes with the next axis will be Z axis will be equal to 0. Because you know that theta is the angle which the vector will make with the Z axis. So when that vector coincides with the internuclear separation or with the Z axis, then theta will be equal to 0. The components of a Pn in the space fixed capital X, capital Y, capital Z coordinate systems are now given. So in this diagram, you assume that this theta is capital theta and this phi is capital phi. So under that condition, and this Pn, this P can be assumed as P naught, or may be assumed as a vector P, Pn, having a component P naught, having a magnitude P naught. So you see that the components will be Px is equal to P naught sine of theta cos of phi, Py will be equal to P naught sine of theta sine phi, and Pz will be equal to P naught cos of theta. You know that in spherical polar coordinate systems, we can find these rectangular components of a vector and the formulas are given over here. Pn for polyatomic molecules. You see that although I am not going to discuss the polyatomic molecules in this lecture, but let's read what it states about polyatomic molecule. The Pn for polyatomic molecule can have any direction, theta and phi. You know that in the diatomic molecule, the value of the Pn is fixed about small z axis. So theta was equal to 0. But you know that this Pn for a polyatomic molecule can have any direction theta and phi. And its transformation to the space fixed coordinate system requires Euler matrix. That is, if you want to find out the components of this Pn in the space fixed coordinate system, which is capital X, capital Y, and capital Z, then of course the Euler transformation is required between the two coordinate systems. And for that one, Euler matrix is required. If the interaction between the rotation and vibration is sufficiently weak, so under the condition that the interaction between the rotation and vibration is sufficiently weak, we can write this wave function. That is the nuclear wave function as a function of capital R, theta, and phi will be equal to the vibrational wave function psi of vibration as a function of R multiplied by Yjm as a function of theta and phi, where y with a subscript of VIB is actually the vibrational wave function, and it is only a function of capital R, whereas Yjm is as a function of theta and phi is actually the angular part of the wave function. And you know that on the left hand side, we are actually considering a nuclear wave function. So in the nuclear wave function, we have two types of a wave function. A nuclear wave function can be specified as a product of the vibrational wave function and the harmonic wave function Yjm, representing an angular part of the wave function, and which is the function of theta and phi. Now you see that the vibrational wave function, which we have all written in one of our previous lectures, that y vibrational is equal to r into s of r, is the vibrational wave function, and it depends only on the value of capital R. And capital Y, Jm, as a function of theta and phi, is the rotational wave function for a rotational level with the quantum number j. And the projection of this quantum number j on the z-axis will be represented by capital M times h bar. And this is the projection on the quantization axis, which may usually take as the z-axis. For absorbing transition, the direction of the incident electromagnetic wave or its E determines the quantization axis. Now you see that here the point is very important. For absorbing transition, the direction of the incident electromagnetic wave or the direction of E determines the quantization axis. So for a molecule, the quantization axis will be determined by, for the absorption case, will be determined by the direction of the incident electric field E. So you see that we can now write d tau n is equal to r square into dr into sine of theta into sine of theta into d theta into d phi. The transition dipole matrix elements as a product of two integrals. Now since we have a wave function as a product of two wave functions, psi vibration and yjm, so we need to write two different integrals for them. So one in the first integral is written for y vibrational, and it contains a p naught, because p naught contains only the value of capital R, whereas p unit vector contains azimuthal part, that is some angles. You know that I have given the value of p naught over here. This p naught contains only the radial part, whereas p hat will contains the azimuthal part or angular part. So I have put the value of p n vector in this integral, which I am going to solve. For example, this vector, this equation, and then you can separate out the two wave due to the two wave functions. These two wave functions, I can write the two integrals. So I have MIK as the integral of one integral is around vibrational state, and the other is along the angular part of the nuclear system. So these two integral are actually the integral of the nuclear part. One contains the vibrational part, the other contains the azimuthal part. And the integral that contains the vibrational part contains a p naught, which I have just shown you, and the other integral which contains the azimuthal part contains the value of p unit hat, p unit vector, or p hat. So the vector p, which I have written as p naught and p hat, is directed along the internuclear axis, and its orientation depends on capital theta and capital phi. The transition probability per second, that is the rate of a probability, that is the derivative of probability for an absorbing transition between the levels ith and kth, is the same in the same electronic state, is given by. So you see that here I am going to calculate the transition probability for the same electronic states, which is given by the rate of p, that is dp over dt, is equal to pi over h square multiplied by e naught square, and then multiplied by the absolute square of this integral, which contains e dot pn, where pn is given by this expression. So pn is equal to, you know, that p naught times p. So you see that I can write dpi dp. So the right hand is written in the same way. I have a pi e square because I have moved e square over here, h bar square e naught square, and then the same integral. And then you see that this constant is represented by capital C, and then the rest of the integral is the same, which contains the chi as the nuclear wave function and chi k as the nuclear wave function. Both corresponds to the same electronic state. And the integral contains the product of E dot Pn, and E is what I have already defined. Pn has also been defined. So C is this constant. So putting the value of C back over here, so I have, you see that these two integrals, one integral will contain P naught, the other integral will contain E dot P hat. So this is P hat, you know. So the P is what I have moved over here. P naught is what I have moved in the vibrational integral, because the P naught contains the radial part. It will not be operated by the angular part. So it can be taken out from the angular part and can be moved into the radial part of the wave, radial part of the integral, which is the vibrational part of the integral. And this integral over here contains P hat. So these two integrals now define separately the matrix values. So the first integral will give you the absolute square of MIK vibrational, whereas the second integral will give you absolute square of MIK rotational. So you see that if you find out MIK vibrational, you can also find out MIK rotational by solving these two integrals. Now you see that I am going to find out the expectation values of Px, Py, and Pz. That is, I am going to determine the expectation values of Px, Py, and Pz. You know that when P is known or its components are known, then it means that P is also known. And once P is known, we can put the values of P and P naught over here in this expression and find out these matrix elements, that is MIK vibrational, MIK rotational. So the expectation value of a Px between the two levels J and M, and J prime and M prime, where J, M is one set of quantum numbers or rotational quantum numbers, J prime, M prime is another set of quantum numbers. So from these three integrals, you can see that the values of first integral contains the expectation value of a Px, the second one is Py, the third one is Pz. And you know that on the right hand side, I have specified the value of a P naught and also sine of theta cos of phi. That is, I have used these three relationships, Px, Py, and Pz, and I have substituted them in the integrals in order to find out their expectation values. The first factor in equation number 205, this factor, the first factor in equation number 205 describes the vibrational transitions from Vi, between Vi and Vk. If V vibrational as a function of R represents harmonic oscillator, then the integral will be 0 unless delta V is equal to Vi minus Vk is equal to 0, or delta V is equal to plus minus 1. That is, we are considering the transition between the same vibrational levels or between vibrational levels which varies by plus minus 1. So if you are putting this constraint on the change of a vibrational quantum number delta V, then of course you can calculate the values of the harmonic for the harmonic oscillator, otherwise the integral will be 0. The plus sign for the absorption transition, the negative sign for the emission transition. Under the given selection rule, only the transitions between the absorbing vibrations, only the transition between the neighboring vibrations levels are allowed for harmonic oscillator. So you see that this plus minus sign with the change of quantum number delta V of the vibrational quantum number, change in vibrational quantum number V by plus minus 1 indicates that if the transition between two consecutive vibrational quantum states will occur, then the integral for the harmonic oscillator will not be equal to 0, otherwise it will be equal to 0. For unharmonic potential, for example, the Morse potential, higher order transitions, though weak, are also possible with the delta V is equal to plus minus 2, plus minus 3, and so on. So you see that for the unharmonic oscillation, we also consider delta V for higher states also. That is, the vibrational quantum numbers may change by plus minus 2, plus minus 3, and so on. The second integral in equation number 202, that is the second integral in equation number 202 or 205, 202, this is the second integral, for example, describes the rotational transition and depends on the orientation of the molecular dipole moment P in space. Of course, the direction of a P is very important in all these integrals. The amplitude of radiation emitted into the direction K is proportional to absolute value of K cross P. Because here we are talking about the amplitude of emitted radiation in the direction of K is proportional to absolute square of K cross P. For absorbing transitions, it is proportional to the scalar product of E dot P, where E is the incident electric field of the incident radiation and P, is the dipole of the nuclear system or the whole electronic molecule, and the intensity will be proportional to the square of this quantity. Now for the figure I have given on page number 130, you can see that E unit vector E dot P will be equal to P naught into Ex sine of theta cos of phi plus Ey sine of theta sine of phi plus Ez into cos of theta, where Ei is the ith component of E hat, and I can stand for capital X, capital Y, and capital Z. And you know that the unit vector E is given by the vector E divided by the magnitude of vector E, where capital E is actually the electric field of E of the incident wave. Angles can be expressed by the spherical surface harmonics YJM. For example, the first term, this symbol states the angle. The first term makes an angle which is equal to cos of theta, and the second term, which is a square root of 8 pi divided by 3 into y1 of plus minus 1, makes an angle of a minus plus sine of theta into e to the power plus minus iota phi. So you can put these values in the previous equation, that is in equation number this, within this equation, and you can express them in the following form. That is E hat dot P vector is equal to P is common, which you have taken outside this one, and the angle is square root of 4 pi over 3, and then the parenthesis contains this term. You see that in order to write down this parenthesis, I have written e to the power iota phi as cos of phi and iota sine of phi. And then I have combined, I have represented sine of phi and cos of phi in their values, and I have written these forms. Inserting this into the second integral of equation number 202, the 202 integral is what I have shown you a minute ago. This is integral 202. So inserting this into the second integral, equation number 202, the angular part of the transition probability integral has the form integral of yjimi y1 raised to power delta m, and then the wave function y of jk mk with respect to delta omega. So this is the integral, and the delta m is equal to 0 plus minus 1. These integrals are always 0 except delta j is equal to ji minus jk is equal to plus minus 1. That is, the rotational transition should only survive between consecutive rotational levels. That is, the kth rotational level is lying close to the jth rotational level. So between these two, that is, the transition between the ji to jk should follow that selection rule as plus minus 1. So if this holds, then these integrals will survive, otherwise the integrals will be equal to 0. The absorption and emitted photon has the sign S is equal to plus minus 1 times h bar, which is the spin of the photon, and the total angular momentum of the system, that is of the photon plus molecule, has to be conserved. So you see that when the photon is emitted or is absorbed or emitted, then of course the spectra, the angular momentum of the photon, which is plus minus 1 h bar, must satisfy that the total angular momentum of the system, that is the angular momentum of the photon plus the angular momentum of the molecule, must be conserved. For the projection quantum number capital M, the selection rules are analogous to the atoms. Delta M is equal to 0 for linear polarization, and delta M is equal to plus minus 1 for the circular polarization of light. So if the light is linearly polarized, it will follow our rule delta M is equal to 0, and if it is circularly polarized, it should obey the rule delta M is equal to plus minus 1. Theta is measured in the molecular coordinate system, and capital theta, capital phi are the angles between the molecular dipole moment and the space quantization axis. Upper state Vkjk is represented by V prime J prime, and the lower state Viji will be represented by V double prime J double prime. So let me show you this in the diagram. For example, this is the diagram, and it represents P and R rotational transitions between the vibrational levels V double prime equal to 0 and V single prime is equal to 1. So here we are considering two vibrational levels shown in green. So the two vibrational levels are shown in green. The lower is the V double prime is equal to 0 vibrational level, which is the lowest vibrational level, and the upper vibrational level is the V single prime is equal to 1. The upper levels will be represented by a single prime. The lower levels, whether vibrational or rotational, will be represented by the double prime. So this V single prime is equal to 1 represented by the green vibrational level, and the rotation below that one I have the rotational levels. For example, a rotational level is represented by J single prime equal to 0, J single prime is equal to 1, J single prime is equal to 2, J single prime is equal to 3. These are the rotational levels lying below the vibrational level V prime is equal to 1. Similarly, I have V double prime is equal to 0, and the rotational levels lying below to V double prime is equal to 0 are J double prime is equal to 0, J double prime is equal to 1, J double prime is equal to 2, J double prime is equal to 3. I have only shown 3 rotational levels for each of these vibrational levels, although there could be many levels. And you know that I have also shown the vibration, I have also shown the transitions between these levels. In the absorption, I have shown the transitions. For example, the transitions in black, which we call as the R transitions. For example, R0, R1, R2, R3, these are the 4 transitions. And these transitions follow the rule that delta J is changing by +1. That is, the change in rotational quantum number is +1. And the other transitions, which is the P branch transitions, I am specifying P1, P2, P3, and P4. These transitions are occurring when the rotational quantum number changes by delta J is equal to -1. So I have two transitions over here. Delta J, for R transition, delta J is equal to +1, and for the P transition, delta J is equal to -1. So you see that when delta J is equal to 0, there will also be a transition which is specified as which is not possible for this molecule. So here you can see that mu naught bar is equal to 0 over here. There is no transition against nu naught. And nu naught is represented in wave numbers. Whereas you see that corresponding to each transition, or branch transition, I have shown the magnitude of these transitions. These, you see that different values of R in magnitude represents the intensity of these transitions. Similarly, I have shown the P transitions with the different magnitudes, and these corresponds to the intensity of these P transitions. There is also a Q transition. You know that here the Q transition is equal to 0. Q transitions mean that the transition when delta J is equal to 0. That is, the change in the rotational quantum number is 0 when we have the Q transition, and here the Q transition is not occurring. That's why we have nu naught bar is equal to 0 over here. So you see that I have specified the upper levels, upper vibrational and rotational levels by single prime, V single prime, J single prime, and the lower levels by V double prime and J double prime. The transition with delta J is equal to J prime minus J double prime is equal to +1 are called the R transitions. And the transition with the delta J is equal to J prime minus J double prime is equal to -1 are called the P transitions. And I have explained them in the figure. Allowed rotational transitions as absorption and emission lines are shown in the figure. And you know that I have just explained the figure. So both rotational and transitions could occur among those levels, giving you the P transitions and the Q, where P branch and the R branches. All rotational transitions in vibrational levels form a vibrational band. So you see that when these transitions occur between the rotational levels of the two vibrational levels, then these are called vibrational bands. And you know that the wave number that we can calculate is given by this. So the wave number or the radiation emitted between the transition between these two set of quantum numbers, V prime, V single prime, J single prime, and between V double prime, J double prime, where V single prime stands for the vibrational level, single J prime stands for the upper rotational level. So these transitions will consist of two parts. One contains V naught bar plus dV prime into J prime plus J single prime plus 1 minus dV prime into J single prime squared V J single prime plus 1 squared, and then the other quantities for double prime is what I have written. V double prime into J double prime and then J double prime plus 1 minus dV double prime multiplied by J double prime squared and J plus J double prime plus 1 squared. So nu naught bar is the band central frequency. It gives a Q line with J single prime is equal to J double prime is equal to 0. That is delta J is equal to 0. This line does not exist in the rotational vibrational spectra of diatomic molecules. That is, the Q lines would not exist in the diatomic molecules. Spectra, rotational vibrational spectra of the diatomic molecules. So there it is missing. The missing line should be over here. Nu is equal to nu naught. So there is no line over here. So you see that this is the figure that I have explained. Now I am just going through very quickly through the text. The rotational quantum number B, the rotational constant BB decreases with increasing V. That is, with a higher value of vibrational quantum number, the value of BB would decrease. For molecules with BE single prime is equal to BE double prime on the transitions with V prime with V single prime is greater than V double prime. That is, we are considering this set of vibrational quantum numbers, then VB single prime should be smaller than BB double prime. And you know that BB is given by BB is equal to BE minus alpha E times V plus half. So you can put the value of alpha E, which is greater than 0, and it is greater than 0 for most of the molecules. Plotting of the frequency V at the value of J single prime is equal to J double prime for P and R transitions as a function of a frequency gives the Fortral diagram shown on the next page. So let me show you that diagram. This is the Fortral diagram. Fortral diagram of the P branch and the R branch of the vibrational rotational transition. So you see that this branch is obtained from the previous diagram. For example, this diagram on the left, this diagram. But you know that here I have shown only only three transitions. Only four transitions I have shown. But you know that if there are 10 rotational levels, for example, then there will be 10 transitions. So each R branch, each dot will indicate 10 transitions for the R branch, and the 10 transitions for the corresponding P branch is given on the left. And there is no Q branch. If the Q branch would have existed, it would be along this vertical axis. So for a diatomic molecule, only we have the P branch and the R branch, and their frequencies which we are and the wave number which we are plotting on the horizontal axis. You can see that how these wave numbers would change with the R branch with the transitions in the R branches. And similarly with the P branch, different transitions are occurring and how their wave number or the frequency would change. So this is called the Fortrat diagram. So the R lines are on the higher frequency side and P lines are on the low frequency side. So in this Fortrat diagram, I am plotting actually the frequencies, not the wave numbers. So these are the nu naught and nu are the frequencies. The vibrational rotational spectrum of the hydrogen chloride HCl with P and R branches are shown in the figure on the next page. The spectrum depends on the reduced mass capital M, and so the lines of different isotopomers are shifted against each other. So let me show you. That is, here I am considering the transition. That is, I am considering the PR transitions, R branch, and the P branch. I am considering 10 transitions for the R transitions and 10 P transitions for the hydrogen chloride with the chloride having atomic mass 35 and also atomic mass 37. I have a mixture of hydrogen chloride in the vaporous form, and then I have recorded this as the emission or the absorption spectrum. And you can see that there is R branch on the right hand side, there is a P branch on the left hand side. But you know that if you consider very closely, each peak contains two peaks, one corresponding to Cl35, the other corresponding to Cl37. So each of these peaks actually due to one is due to two isotopomers of chloride. One is chloride 35, the other is chloride 37. The caption of this one is vibrational rotational absorption of the hydrogen chloride 35 and hydrogen chloride hydrochloric acid 35 and 37 isotopomers in the infrared region with the lambda varying from 3.3 to 3.7 micron. So actually this is the end of lecture number 18J. The lecture is continued. There will be at least two more lectures on the molecular physics part, on the molecular physics side of diatomic molecules.